Here we're going to solve Leetcode problem 50, POW xn. In this problem, we are tasked with finding a way to calculate x to the power n with the following constraints. Negative 100 is less than x, which is less than 100. Negative 2 to the 31 is less than or equal to n, which is less than or equal to 2 to the 31st power. And negative 10 to the 4th is less than or equal to x to the n, which is less than or equal to 10 to the 4th. So normally, in a problem like this, what we'd look to do is we'd just go with a simple for loop from 1 to n and multiply our variable answer, which is originally set to 1, by x each time. This will lead to a total value of 1 multiplied by x n times. The pseudocode I wrote is right here. We have an original value of nth, which is 1, and for I in range n, we just multiply our nth times x. And however, in this problem, we're given our constraints is n is less than or equal to 2 to the 31, which means our for loop will take too much time and will be too expensive for our program. To solve this problem, we have to find a faster method to multiply all of these numbers. And to do this, we can use a method called Binary Exponentiation. In this technique, we're going to use two main facts. Our first main fact in this method is that x to the n is equal to 1 over x to the negative n. Our second main fact is that if n is even, x to the n is equal to x to the n over 2 times x to the n over 2. And if n is odd, x to the n is equal to x to the power of floor of n over 2 times x to the power of floor of n over 2 times x. What we're going to do here is we're going to split up our case into a few main cases. Our first main case is that if n is less than 0, then x to the n is equal to 1 over x to the absolute value of n. So in this problem, we can write our large function called final POW, which returns the value of if n is negative, then it will return the value of our answer to be 1 over x to the power of absolute value of n. Otherwise, if n is greater than 0, then our answer is simply x to the power of n. Now we'll move on to the meat of our code. The main part of our code is we have to write a fast POW function that does our binary exponentiation. And in this function, it'll take in two values, x and n. But n is greater than or equal to 0, as we wrote in our final POW function. Our x and n have the following constraints as we stated at the beginning of the problem. We know that x is greater than negative 100 and is less than 100, and n is greater than 0 and is less than or equal to 2 to the 31 minus 1. In this function, we have to clearly set up a base case. So in order to do so, we have our base case to be if n is 0. Any number to the power of 0 is 1. So if n is 0, we'll just simply return 1. Otherwise, we'll move on to the rest of our code. Here, we're going to use the same cases we talked about earlier. If n is even, then x to the n is equal to x to the n over 2 times x to the n over 2. So in our pseudocode, if n mod 2 is 0, or n is even, then what we'll do is we have our total power to be equal to fast POW of n over 2 times fast POW of n over 2. So basically, x to the n is equal to x to the power of n over 2 times x to the power of n over 2. Our other case is when n is odd. So our other case, x to the n is equal to x to the power of floor of n over 2 times x to the power of floor of n over 2 times x. So here we have our total power to be equal to fast POW of x comma floor of n by 2 times fast POW of x comma floor of n by 2 times x. And then we'll just return our total power. However, we did forget about one case at the very beginning in our final POW. We forgot about the case where x is equal to 0. If x is equal to 0, then x to the n is always going to be 0. So then we'll include that in our final POW as our case. If x is 0, then we'll always return 0. Now that we've dealt with all the cases of this problem, we can move on to the code. In the code, we're first going to define an outer function called finalPow that will return a double value. And in this function, it'll take in two values, a double x and an integer n. Our first case is if x is 0. Clearly 0 to the power of any number is equal to 0, so we'll just return 0 in this case. Our second case is if n is less than 0. Then what we'll do is we'll return 1 over x to the power of absolute value of n. So in this case, we'll return our 1 over our fastPow of x, comma, absolute value of n. FastPow is a function we'll define later to calculate powers of n being greater than 0 quite fast. Our final case is if n is greater than 0, then clearly we'll just return the fastPower of x, comma, n. So we'll just return x to the power of n. Now we'll define our fastPow function, which returns a double and takes in two values, a double x and an integer n, which is greater than or equal to 0. In this function, we'll take a base case. If n is 0, we'll just return 1. Now we'll set an answer variable. So we'll just set a double answer variable to be a dummy value, such as 1. Then our first case is if n mod 2 is 0. In this case, we know n is even, so x to the n is equal to x to the n over 2 times x to the n over 2, which will be shown in the code. So we'll set a double halfPow, which will be equal to x to the n over 2. So our halfPow will be equal to the fastPow of x, comma, n by 2. And our answer will just be equal to our halfPow times halfPow, because our x to the n is equal to x to the n by 2 times x to the n by 2. Our final case is if n mod 2 is 1, or if n is odd. Here we'll set a double variable called halfFloorPow, which will be equal to x to the power of floor of n by 2, which is also equal to fastPow of x, comma, floor of n over 2. Then we'll write an answer variable called, which will be equal to halfFloorPow times x, because x to the power of n is equal to x to the power of floor of n by 2 times x to the power of floor of n by 2 times x. Finally, we'll just return our ans. Now we'll try to test our code. The first test case we'll try is we'll try to print the value of finalPow of 5, 4. So the value of 5 to the 4 should be equal to 625. And let's see what we get here. 5 to the 4th is equal to 625, which is clearly the correct answer. Next we'll try 0.5 to the power 2. 0.5 to the power 2 is clearly 1/4, or 0.25, which is the answer that we get. One more case we can try is 0.5 to the negative 2. 0.5 to the negative 2 is equal to 1 over 1/4, which is equal to 4, which is exactly what we get. We see that our code works and is done. So we have a working power function that runs in log n time.